you, Cosmos. Our third team is Firebird Sora from Seisen International School in Tokyo, Japan. Their innovation, Hydroshield 15, is a fabric that protects the astronauts from the cosmic rays and electromagnetic radiation in outer space. Please welcome Firebird Sora.
In 1961, Yuri Gagarin became the first man to travel to space.
1969, Apollo 11, the first manned mission to the moon, became a reality.
1998, the International Space Station was launched, the largest man-made body to ever be brought to space.
So what's next? With the recent development of technology, it will soon be possible to send astronauts into outer space for longer missions outside of the Earth's protective magnetosphere. We'll finally be able to explore outer space to gain a greater understanding of what's out there. We'll be able to travel to Mars. We'll be able to explore the solar system and beyond.
Whoa, slow down. I think you're getting a bit ahead of yourself. How are astronauts supposed to travel so far when outer space is filled with dangerous particles called galactic cosmic rays?
Galactic cosmic rays are hazardous particles in outer space, which primarily consist of protons, as well as alpha particles and HC ions, which travel at high speeds. Even though exposure to galactic cosmic rays leads to significant health damage, such as cancer, DNA mutation, and circulatory disease, the current EVA suit provides little to no protection against GCRs. Clearly, this is already a huge problem, as it is detrimental for the health of the astronauts traveling to outer space, but will continue to become even more significant with longer space travel missions, such as the mission to Mars. As can be seen from the table, even short missions to outer space have a negative impact on the human body.
Our solution? Hydroshield 15, a unique product to protect astronauts from the harmful galactic cosmic rays. Hydroshield 15, as the name suggests, is made up of materials that are high in hydrogen atoms: polyethylene, polyester, polyaniline, and hydrogel. The special feature of our product is that it combines polyethylene, polyester, and hydrogel effectively through the use of polyaniline, making it possible to use hydrogel and hydrophobic materials simultaneously. Then, what is the benefit of using materials that are dense in hydrogen? Well, as most people may know, hydrogen is the smallest known atom. Due to its size, hydrogen atoms can be more densely packed into a set amount of space than any other substance. Consequently, there is a higher probability of the high-energy protons colliding with one of the hydrogen atoms. In addition, hydrogen does not create secondary radiation, unlike other elements with high atomic number, often used in radiation shielding.
This diagram shows how exactly Hydroshield 15 will block the protons in the galactic cosmic rays. As a proton collides with the hydrogen atom, a part of its energy is transferred in the moment of contact. After that, it collides with another hydrogen atom in our product, repeating the same process, and eventually loses most of its energy through the multiple collisions. Here we have taken a proton with a high energy of 100 mega-electron volts and calculated its remaining energy as it passes through the layers of Hydroshield 15. As you can see, the proton loses a substantial amount of energy as it collides with the hydrogen atoms in our product. According to our theoretical values, the effects of the proton can be minimized with 10 layers of Hydroshield 15, thus protecting the astronauts from the galactic cosmic rays.
To provide a clear image of how exactly our product will be incorporated in the EVA suit, here is a model of where and how it will be placed. A single layer of Hydroshield 15, which is 4.3 millimeters thick, is very flexible and can easily be incorporated in the current EVA suit. So, we are hoping to incorporate 10 layers of our product between the mylar and ripstop layers for a sufficient amount of protection.
So why choose Hydroshield 15?
Well, our product consists of materials that are low in cost and accessible compared to other products designed to achieve the same goal. In the current stage, a single layer of Hydroshield 15 is expected to cost around $2,254, meaning that even with 10 layers incorporated in the EVA suit, it is expected to only cost around $22,540.
Although the cost will most likely be higher due to the amount of research and funding required for our product, It is still low compared to the hydrogenated boron nitride nanotube, which is another material known to show similar shielding effects. It is estimated to cost $475,000 for only one layer and requires special technologies in its synthesis, making it difficult to create a finalized product in the near future. Electrostatic and magnetic shielding concepts are also under construction, but the complex magnets and billions of volts necessary to create even a simple shielding layer make the entire concept seem overly problematic in comparison.
To produce Hydroshield 15, the next immediate step would be to further test and research a product to confirm the concept, as well as to make the product more lightweight and effective. In order to do so, we are mainly looking to cooperate with research grant organizations, as well as space agencies such as NASA and JAXA. Although we recognize the extensive cost and research required to finalize a product, we are confident that Hydroshield 15 is worth investing in, as it is 1. Inexpensive, 2. Protective, and 3. Effective.
The potential of Hydroshield 15 is limitless. Just imagine the new era where humans are able to travel in outer space without having to worry about
certain death.
Okay, maybe that's a bit intense, but Hydroshield 15 can definitely protect astronauts from otherwise inevitable health problems. The mission to Mars no longer has to be a dream. With Hydroshield 15, astronauts can travel outer space longer,
further, and safer.
2017. Hydroshield 15 was created by 4 high school students
determined to make a change.
So I want to say a great job, great presentation on defining the problem, developing a solution. Very serious problem that you guys are tackling. So great job, again, on defining what the problem is, developing a solution, and then demonstrating how this could or should be integrated. Good job.
Great concept, definitely needed in future space missions. I want you to expound on, now that the concept's defined, how you're going to test it and how you're going to send the protons or gamma rays into the material and ensure that 10 layers is actually sufficient opposed to just model-based analysis. But great job.
Yeah, very important stuff you're tackling. I'd like to see more comparison with other suggested solutions, and less emphasis on the cost, because when you're talking about a $60 or $600 billion mission, a few $1,000s for radiation protection doesn't really come into it. So I wouldn't really focus on that. Also, it's not just the spacesuit, but also the entire spaceship that will need protecting. So you could put some focus on that as well. But interesting concept, and I look forward to hearing how it tests out. Thanks.
Good job, very well presented. I'm happy that you guys are thinking at par with NASA. NASA is thinking to go to outer space, and so you are. So you're no more limited to the moon and the lower orbits. Very well presented. There's one thing which was missing was the weight comparison. Now you said that we need to have 10 layers of 5 millimeter, that is 50 millimeter plus the mylar, 10 layers of mylar. So it's going to be very bulky. So you have to do the weight comparison as well, and how it is done today, how the astronauts are protected today, and how beneficial is your technology with the current one. That data is also needed. Other than that, you guys are going great. Thank you.
Yeah, really well done. Nicely done, ladies. Seriously, very well presented. Most of the comments I had were already taken up by my fellow judges here. The only other one that I would add is it might be worth exploring. You mentioned that the risk once you leave the protective element of the Earth's magnetic field, the risk goes up once you leave. It'd be interesting to see a graphic of exactly by how much. In other words, how much of a problem. And that's relevant because if you're going to compare it to the way spacesuits are protected today, well, that may be fine for astronauts working in low Earth orbit, but how much different is that risk? How much more radiation is there once you leave, and how far do you have to go? It'd be interesting to see a graphic to go. Once you get so many millions of miles from the Earth, the risk begins to go up as it would be interesting to kind of see an element of how much of a problem is this really compared to what they're dealing with now. But well done.